Hi there, folks. This is the 5.1 to 5.3 practice worksheet. And as always, I am the amazing Mr. Jansen. So away we go. If we look at something like this, we're looking for increasing and decreasing behaviors. We're also looking for relative maximums and minimums. And then we're also going to look at end behavior on these things. And when we're looking at a graph, when we're talking about increasing and decreasing, we're always working left to right as we read this. And just think of decreasing as a negative slope, increasing as a positive slope. So right here, the function would be decreasing here because it's headed downwards. And then it would change directions and start increasing. And then it would change directions again and decrease. And then it would change directions one more time and increase for the remainder of this thing. Okay? So that's what we're talking about when we talk about increasing and decreasing. So if I look at the increasing, the things that are in green, I want the intervals over which this is increasing. In other words, the x values. It increases from here until here in terms of my x. So it increases from the value of -3 to the value of 0. And in interval notation, neither of those is included because each of those, it kind of caps out at a local max or min. So neither of those values is included, so I use parentheses. And then the other interval where this thing is increasing is from here to wherever. Okay, so it starts increasing again at +3 and keeps increasing for the rest of the function, which is until +infinity in terms of my x. Okay, once again, I'm going to use parentheses for each of these because there's no way to indicate that those values are part of the increasing or decreasing because they're not. And then I put a union symbol in between because it's increasing on each of these, so I want them to be associated with one another. Okay, decreasing is what we have highlighted in red here. And again, when we're decreasing, we're going to look at the values for which this is decreasing. Well, the x values, the word it's decreasing, is from here on over. Or really, I have to think of in reverse. From here, out in this direction, that's -infinity. So from -infinity until -3, this thing is decreasing. Let me try that infinity symbol again. That looks a little bit better. So it's decreasing from -infinity until -3. And then it's also decreasing from here to here, which is the interval from 0 to +3. Again, we're always working left to right. There's no inclusion here in terms of those x values, and then I put a union symbol in between, and that's it. Okay? Relative max just means it's a maximum relative to the points around it, so I'm basically looking for a high point here. And if I'm looking for a high point, the only high point that I see relative to the points around it, other than when I go to infinity, are these values right here. This point right here is higher than the points around it. It's got a little bit of a high point there, so we call that a relative max, and that's at the ordered pair 0, 0. And keep in mind, increasing and decreasing, that's interval notation. Relative max, that's an ordered pair. In terms of a relative minimum, there's two of them here. There's two low points on this function. There's two spots where there's a point that's lower than the points around it, and that would be this point over here at -3, -4. And then this point right here at 3, -6. And again, I just list each of those because we're talking about something that's, let me scoot that guy over here. So we have two of them here, the -3, -4, and the 3, -6. They're both relative minimums because they're minimum relative to the points directly next to them. Okay? In terms of end behavior is always defined as what the function is doing as x goes to -infinity. And as x goes to +infinity. Okay, so I just start with those two values, and then I just look to see what y is doing. When I talk about x going to -infinity, I'm essentially talking to the far left of the function. So I just look at the arrow on the far left. So right here, I'm looking at this arrow on the far left, and it shows me that the function is going up, and the arrow indicates that it does that forever. So f of x would be going up forever, which is going to +infinity. Okay? And then when I look at x going to +infinity, essentially I'm looking at the far right of my function, which is right here. I look at the arrow, I see what the end of the function is doing, and it looks like it's going up forever, so f of x goes to +infinity in that direction as well. All right, and that's it. If I look at the next one, I'm doing the same thing, increasing and decreasing, positive and negative slope. So it starts off, it's increasing until I get to here, and then it's decreasing after that. And then it's increasing after that. Okay? So it starts off increasing and then it's decreasing. And again, these values, it's not increasing or decreasing. It's kind of leveled off. Okay? Those are our local maximums and minimums. So increasing, again, the x values, From here over, it's increasing. So again, that starts at negative infinity and goes up to a negative 2. So it's increasing from negative infinity to negative 2. Neither of those values is included again because, again, it levels off in there somewhere. It's not increasing or decreasing. And then from here on up, it's also increasing. So from positive 1 to positive infinity. And I put my union symbol in between. And then decreasing, there's only one spot that it's decreasing. It's decreasing from here to here in terms of my x values. So it's decreasing from the negative 2 to the positive 1. And that's it. And again, that's interval notation. When I do the relative max and a min, these are going to be ordered pairs. And it looks like I have a relative maximum right here. It's a high point, higher than the points around it. And that's at negative 2, 3. Again, that's an ordered pair. And then a relative minimum is right here. It's a minimum relative to the points around it. And that's at the ordered pair 1, negative 3. And then once again, my end behavior, I always start off the same way. I'm looking as x goes to negative infinity, and I'm looking as x goes to positive infinity. And then I just see what my f of x is doing. I see what y does on each end of the function. So when I'm looking at x going to negative infinity, again, that's the far left of my function, which is this end right over here, and I look at the arrow. What's it doing? Well, it's going down, so my f of x is going to negative infinity as well. All right? When I look at x going to positive infinity, I'm looking at the far right of the function. So I look at the arrow that's on the far right. I look at this end, and it's going up forever. So f of x is going to positive infinity here. And that's it. Okay? That's what we're doing when we talk about end behavior. Okay? For these, when I'm looking at to find end behavior algebraically, essentially what I'm going to do is I'm going to plug in a positive infinity, and I'm going to plug in a negative infinity. So I'm still looking as x goes to negative infinity, and then as x goes to positive infinity. Again, that's just the definition of end behavior. When I have it in standard form like this, in other words, when it's separated into terms, I just, instead of plugging into each of these x values, I just plug it into the highest exponent in terms of my terms. Okay, so I find the term that has the highest exponents. That's the one I used, because this thing is increasing so much faster than everything else that it's the only one that matters. And so when I plug a negative infinity in here, so I've got to the 7th power, and I'm going to plug a negative infinity in. Well, negative infinity to the 7th power is a negative infinity. So now I have a negative times a negative, which is a positive infinity. So as x goes to negative infinity, f of x goes to positive infinity. And really, we're just playing a game with the signs here in order to plug this thing in. And now I do the same thing with positive infinity. I've got a negative x to the 7th, but I'm plugging a positive infinity in this time. And when I do that, positive infinity to the 7th power is infinity. And now a negative times the infinity gives me a negative infinity. Okay? And that's my end behavior, and I have to have it written this way. All right? If I look at the next one's not written in standard form, so I can't ignore any piece of this. I can't see where my highest exponent is. In this one, the highest exponent is actually going to be an x to the 5th, but I can't see that because this isn't written in standard form. It's not in terms of the terms. So I have to plug the x value into each of these. But I still start out by doing x going to negative infinity and x going to positive infinity. And I'm just going to plug it into each of these. So if I plug the negative infinity in, again, it's a negative x squared. Infinity plus 3 is still going to be infinity, so I just treat it this way. And then I have another value squared. So I plug these negative infinities in. And again, I kind of ignore the plus 3 because a negative infinity plus 3 is still a negative infinity. I ignore the 2 and the minus 1 because it's still going to be a negative infinity. Really, it's a game that deals with the signs here, so all I care about is the exponents. If I look at this first one, negative infinity to the 2nd power is a positive infinity inside my parentheses. This is a negative infinity. And then, again, a negative infinity squared is going to be a positive infinity. So now what I have is a negative infinity times a negative infinity times a positive infinity. Negative times a negative is a positive, times another positive is also a positive. So f of x is going to positive infinity. Okay? And then I do the same thing with a positive infinity. I'm going to plug that in. So again, it's a negative value squared times the next value times another value squared. And I'm plugging infinity in this time, the positive version. So when I do that, infinity squared is infinity, and then I tack on this negative sign right here, times a positive infinity times infinity squared, which is infinity. And now I've got a negative times a positive, which is a negative infinity. So f of x is going to negative infinity. Okay, and that's it. Let me redraw that sign. That's a terrible looking infinity sign, Mr. Jansen. So again, be aware of the notation that we're using here. Make sure you're writing that out appropriately. Okay? For the next one, it asks us to write the solutions, state their multiplicity, and then state whether it crosses through the x-axis or touches the x-axis as we're going to graph these things. So again, I set each factor equal to 0. I do x equals 0. I do the x minus 3 equals 0. And I do the x plus 4 equals 0. And I just solve each of these. Okay, this one's already solved, so x equals 0. And this one I would add the 3 to each side, so I'd find out that x equals 3. This one I would subtract the 4, so x equals a negative 4. All right, these are my solutions. Okay, so my solutions are here. Again, those are the x-intercepts. And now if I want to state the multiplicity, when we're talking about multiplicity, we're talking about how many times each of those solutions would occur. So if I look at the x equals 0, I only had one of those x's up here in the function, which means that would only occur one time. So the multiplicity for this first one is 1. The second one, I have an x minus 3 to the 4th power. In other words, that x minus 3, I would have that 4 times. So in other words, I would get that solution of x equals 3 4 times, so the multiplicity here is 4. And then the last one, the x plus 4, is being raised to the 3rd power, which means I would have that x plus 4 3 times, which means I would get the solution of x equals negative 4 3 times. All right? And then in terms of how this reacts with my graph, in terms of my x-axis, when the multiplicity is odd, the function's going to pass through or cross over the x-axis. When it's even, it's just going to touch. So this one is going to go through. This one's just going to touch. And this one's going to go through. All right? And that's because of the multiplicity here. When the multiplicity is odd, it passes through. When it is even, it just touches. Okay? For number 6 here, we're doing the same thing. I said each factor equals 0. The first factor is just an x, so I said x equals 0, the x minus 4 equals 0, and the x plus 3 equals 0, and I solve each. This one's already solved. This one I add the 4 to each side, so I find out that x equals 4. This one I subtract the 3, so I find out that x equals negative 3. And now I want to talk about the multiplicity. That x was being raised to the 3rd power, which means I would get that solution 3 times, so the multiplicity here is 3. The x minus 4 was being raised to the 6th power, so I'd get this solution 6 times. And the last one was being squared, so I would get this solution twice. Okay, so that's my multiplicity, and that tells me about the graph. This one is going to pass through the x-axis. This one is just going to touch the x-axis. And this one's also just going to touch the x-axis. Again, when the multiplicity is odd, it passes through, and the multiplicity is even, it just touches. All right?